Hello viewers, in this session we are going to talk about the real-time simulation of electric vehicles. Particularly, I am going to talk about the FPGA based electric vehicle modeling and simulation developed by OPAL. Before we go more into the modeling, first I would like to briefly introduce about the simulation software platform and the hardware that we have used to make this modeling exercise. As you can see here on the left hand side, OPAL has different simulation software tools ranging from tools which can do large scale power grid simulations like ePhasor sim, which run at a higher time step, to something like an eFPGA sim, which is typically a power electronic simulation run on FPGA, focusing mainly on low time step for a high fidelity and high accuracy smaller systems. So eFPGA sim is the tool that we have used in this application. With regards to the hardware, the figure on the right hand side shows the different real-time simulation platforms that we have. So for this particular exercise, we have selected the OP4510 hardware simulation platform. Coming to the modeling, the figure on the right hand side shows the different subsystems of an electric vehicle. So we have the energy source subsystem, the electric potential subsystem, and the auxiliary subsystem. The energy source subsystem involves the energy source, which is in the case of battery electric vehicle mainly the batteries, and the energy management units. The energy subsystem interacts with the electric propulsion subsystem through a power converter. The brake and the accelerator of the electric car gives inputs, the driver's inputs, to an electronic controller which determine the amount of torque needed for the vehicle. So the amount of torque is controlled through a power converter which interfaces with an electric motor and which in turn drives the mechanical transmission of the wheels. So the auxiliary subsystem involves the other auxiliary systems of an electric vehicle like temperature control unit, power steering, auxiliary power supply, etc., which are the inputs taken from the steering wheel. So on a high level, we can say the major components needed for a modeling of an electric vehicle are energy source, which in this case is a battery, a electric motor, power converters, energy management unit, mechanical transmission, and vehicle body. So I will start with the first component, the most important component, the battery. So the slide here shows the modeling of a generic battery. So battery is usually described as a set of multiple nonlinear equations. So depending on the kind of fidelity required, the battery can be modeled as a simple way, or it can be more detailed or more advanced. A simple model like what I am showing in this figure here just takes into consideration the potential of a battery, the open circuit potential, and depending on the internal resistance and the current drawn, how the battery voltage changes. Now the issue with this model is it's overly simplified and it does not completely consider the various dynamics within a battery. So there are other models also which were developed, like for example the detailed model that I am showing here is by Professor Wu and Dogel, and here the dynamics of the battery, like the state of the charge and the impact of the temperature and equilibrium potential, are considered in making the battery model. Again, the state of the charge depends on the battery capacity and the discharge current. So that is a detailed model. Again, the disadvantage of this model is a more linear model when compared to the other kinds of models which are often used. The third type of modeling, which is like an advanced modeling, is as I'm showing here in the screen below. So the battery here is represented by a series and parallel combination of resistors and capacitors. Now the point here to note is the parameter values of these resistors and capacitors keep changing based on the multiple conditions and different operating criteria. It is a very complex model driven by the different parameters, taking into consideration the different dynamics of the system. In this particular example, we have taken this particular model, the advanced model for simulating in the battery, for the battery electric vehicle. The only point to note here is, for the sake of simplicity, we have considered the parameter values to be constant. The figure on the right hand side shows the model developed in MATLAB of the battery. The next component is the motor. The commonly used motor for an electric vehicle application are brushless DC motor, permanent magnet motor, induction motor, and switched reluctance motor. So of this, permanent magnet motor is one of the most used. So in this lecture, I am going to talk about the modeling of permanent magnet machine. So a permanent magnet machine, the equivalent circuit of it is shown in the left hand side, and as we all know, the state equations describing a motor are relates the flux of the machine with the voltages and currents is given on the right hand side. So the electromagnetic torque generated by the motor is given by this particular equation. So the permanent magnet motor along with the state space equations describing the machine were developed in MATLAB. The next component is the powertrain. The vehicle dynamics influence the overall vehicle performance. A vehicle needs to overcome several resistive forces to obtain traction. As I am showing here on the figure left hand side, there are three different types of forces which act on a vehicle when it is moving. The first is the aerodynamic drag represented by Fr. The second is the rolling resistance, and the third is the grade resistance when we are moving on uphill. So the modeling of a powertrain is given by these set of equations, and accordingly based on these equations a MATLAB model was developed which is shown below. The fourth important component is the voltage source inverter. The voltage source inverter is the heart of the system, and it controls the amount of torque that needs to go to the mechanical subsystem for the proper traction of the vehicle. Voltage source converter was modeled in MATLAB using EHS, electric hardware solver of OPAL. So the EHS enables the real-time simulation of power converters effectively on the FPGA system. In this slide, I am showing the implementation, the real-time simulation of the electric vehicle. The electric vehicle simulation is divided into two parts. The entire electric vehicle is made in one hardware platform, the OP4500 platform of OPAL, and the controller is implemented in the same OP4500 on a different hardware. So it's basically two different hardwares interacting with each other. In the first block, the blue block where the electric vehicle is implemented has again two different subsystems. In the first subsystem, the mechanical powertrain and the battery model are implemented, and they run in the CPU core of the hardware at 20 microseconds. In the second subsystem, the power electronics and the machine are implemented on the FPGA, and they run at 500 nanoseconds. So running this power electronics and PM on the machine at a lower time step allows us to capture properly the dynamics which are happening within the machine and within the power converters. These four subsystems through the analog input and outputs interact with the OP4500 controller. The controller is implemented on OP4500 platform, which uses Kintex FPGA board using RTXSG and Xilinx system generator software. The use of block connection based programming tools greatly simplifies the implementation of the controller on FPGA. The flux observer part of the controller computes the stator flux based on stator currents and voltages and reconstitutes from switches gates. Direct torque control is the control mechanism used in this particular application. The principle of direct torque control is to select appropriate voltage vector according to the stator, magnetic flux, amplitude and position, as well as the error between reference and actual torques. This shows the implementation of the direct torque control along with the state vector implementation in eFPGA sim using EHS. As mentioned earlier, the direct torque control in this example is implemented in FPGA. The controller receives the reference torque, flux values and other values necessary for the controller. The analog input-output subsystem monitors the analog outputs to be sent to the DTC controller simulator, like the motor currents and the electric angle to be used for flux estimation. The direct torque control block also receives these inputs and determines the necessary gating pulses for the power converter. The next slide shows the simulation analysis of this model developed. In the first simulation corresponds to the case where the vehicle accelerates until the speed of 80 km per hour at 38 seconds, and then the vehicle goes on a slope of 8% at 39.5 5 seconds. You can see different motor entities like the phase currents, the voltages, vehicle speed and electromagnetic torque are shown in this picture. The second simulation corresponds to the case where the vehicle accelerates until the speed of 80 kilometers per second at 33.5 seconds, and then at 35 seconds starts decelerating to 50 kilometers per hour. We can observe the change in the motor entities like currents and voltages when compared to the earlier case, and also the changes in the battery current and voltages when compared to the earlier case. These two simulation cases shows the performance of the electric vehicle under varying reference speeds as given by the driver. As a summary, in this session we looked into the real-time modeling and simulation of an electric vehicle. Particularly, we looked into the detailed modeling of important components of an electric vehicle, the implementation of the electric vehicle in hardware, and we also looked into the couple of simulation case examples on how on the performance of the electric vehicle under varying conditions. Thank you.